Yes. Katerina has got struggling to get her Wi-Fi to share.
I did send it.
Oh, you did send it.
I think I sent it to everyone from 1 to 3 session. Yes, you sent? Yes. Just like 5 minutes ago.
Okay. So we had a go to put a few down because we were a bit confused. Oh, this with us. It's not. This is them.
Yes, this is them.
Yes, and then we're which makes much more sense.
Yeah, so because I collected also maybe some things that came up in other sessions, we can check and then of course after the session.
Yeah.
Because I remember them. But
Okay, who's the first speaker? Hi, Louise. Okay, you're set. Hopefully. Yeah, I've checked. I think they've got all the files. We'll give you a nod when it's 15 minutes.
okay.
And then, we'll get the book out.
No problem with that.
At some point. But we'll tell you when it's 15, so you've got
Okay.
to go. Okay. Right. Good afternoon, Leeds. How are you all doing? This is the first of 3, I think, Earthquakes and Tectonics sessions. We're going to be chairing this. I'm going to introduce the first couple of talks. Then Katerina is going to introduce the remaining talks. So without further ado, the first speaker is Louise Maubon. Over to you.
Hello, everyone. Hello, everyone. Today I will discuss the importance of using INSAR data in mapping subduction zone, and I will show you the example of the coupling over the Ikurangi subduction zone. So the seismic cycle can be described as a loading phase, which is called the interseismic. This phase is when the stress is accumulated over the interface between 2 plates, and at first approximation, we can observe in geodetic data a linear trend. We observe that in this station here. So using the surface deformation, we can calculate the coupling map, which is between 0 and 1, and a region which be coupled, like we can observe in this map, in red here. Sorry. More it will have the potential to release stresses in seismically form. But today, we know that the seismic cycle is more complicated than that, and we know that transient deformation happened in the seismic cycle. These transient deformation are not hazardous for people, but what is the impact of on the plate coupling? So the first scientific motivation we wanted to answer with this study is if the deformation evolved through time, which observational period should we choose to recover the plate coupling? Shall we use the long-term period with more than 10 years of data? Shall we use the period between long-term slow slip event or the period between every slow slip event? The second question is, by looking at different time periods, can we determine a kinematic coupling, and can we determine if a region will release stresses aseismically or seismically? And finally, the spatial extent of coupling is directly linked to future seismic hazard, but does GNSS provide sufficient resolution to accurately recover coupling? So to answer to this question, we propose to do a geodetic study using GNSS and INSAR time series with Sentinel-1 images. And then we propose to do a geodetic inversion to retrieve the slip deficit on the interface and then the plate coupling. So here we study the Ikurangi subduction zone, which is situated beneath the North Island of New Zealand. This region is very interesting because we have several slow slip events which happen there. On the East Coast region, these slow slip events are shallow and short term. They happen every 6 weeks to 12 months. We also observe deeper and longer-term slow sleep events in Kapiti and Manawatu region. This event happened every 4 to 5 years and with an equivalent magnitude of 7 to 7.5. So on our study, we used 92 GNSS stations. We didn't take account of the GNSS station in the topo rift here because they are sensitive to the volcanic deformation and we want to observe only the subduction signal. We used two Sentinel-1 tracks, one in ascending and one in descending. We use long temporal baseline to mitigate biases in our time series. We correct the interferogram using ERA5, and we construct a time series using a small baseline approach. Finally, when we obtain the time series, we want to extract the linear velocity associated to the subduction. For that, we use a trajectory model, which is very simple. We describe the displacement as the sum of a linear trend and the constant. But on this GNSS time series, we can observe that the observational period we will choose will strongly impact the velocity we will recover. So the next step is to choose the period we want to study to determine the plate coupling. We can study the long-term period, which is between 2006 to 2016. So we observe very well here that the slow sleep event will impact the linear velocity estimation. We didn't take account of a longer period because there is a Keikura earthquake which happened in November 2016, and we don't want to take account of this earthquake and the following post-seismic. We can also study the inter-deep slow sleep event, which is the period between slow sleep in Manawatu and Kapiti area. Using this period allows us to observe 4 years of the seismic cycle between 2018 and 2022. But we can observe on the north that the GNSS time series will be impacted by shallow transient deformation. However, if we look at the INSAR time series associated to this region, we observe a very good correlation with GNSS data, and we also observe that we will be able to retrieve velocity which will be coherent because we have enough dates. And then we can also observe the inter-slow sleep event, which is the period between every slow sleep event. This period will be between 9 months and 1 year. So the problem by doing that is we will need different period window for every region of slow sleep events, and it will be very difficult to estimate a velocity in region with short-term slow sleep events using INSAR data. So like we can observe here, if we want to estimate a velocity in this period, we will be strongly impacted by a seasonal signal. So also, it will be very difficult or quasi-impossible to determine a coherent velocity and vertical displacement on the GNSS data due to different noise such as the seasonal signal. So instead of doing that, we choose to study the inter-major slow sleep events. So we can observe that there is slow sleep events which are bigger than other. And this period allows us to observe 2 years of the seismic cycle, which is enough to obtain coherent velocity over our INSAR time series. So just to summarize, we have 3 options. The first one is to study 10 years of the seismic cycle, but using only GNSS data because we do not have INSAR during this time period. The second option is to study 4 years of the seismic cycle between deep slow sleep events with GNSS and INSAR data. And finally, the third option is to study 2 years of the seismic cycle using also GNSS and INSAR data. So here are the results for the 3 options we have of the GNSS velocity estimation. What we can observe, it's during 10 years, we have smaller velocity in our GNSS linear estimation than during 4 years or 2 years. It's what is expected because 10 years of of observation, is impacted by slow sleep events in almost everywhere in New Zealand. If now we look at our INSAR data, so on the left are the velocity map over 4 years of observation, and on the right is the INSAR time series for the station TAC. So first we observe a very good correlation between GNSS and INSAR data. We also observe that we are able to detect the slow sleep events in the Manawatu region. So we do not have the beginning of this event because Sentinel-1 began after the slow sleep, but we can recover the end of the event. And what we can observe we have a good estimation of the velocity during 4 years of observations. If now we look at on a station which is located on the shallow slow sleep event area, we also observe a good correlation between INSAR and GNSS velocity, but it's interesting to notice that we are not able to observe slow sleep events in this region. The slow sleep events here are small in amplitude, and there is almost no vertical deformation associated with these events. So finally, we need to correct our time series from the plate model. So we decided to convert our time series in the block model, which has been published by Wallace et al. In 2010. And what we observe is when we correct our ascending data, we remove almost every deformation because most of them is associated to an horizontal displacement due to the rotation of the North Island. If we do the same correction on the descending track, we still observe the same pattern before and after correction because descending track are less sensitive to horizontal displacements. Finally, if we compare our different data sets between 4 years and 2 years to validate our results, we observe that we have some residual ramp in INSAR data, and we also observe some unwrapping error, like here, in our velocity estimations. If we compare GNSS time series over 2 years and 4 years, we observe that only this part of the subduction zone is impacted by the slow sleep events, the shallow slow sleep events. So finally, now that we have all these data sets, we can perform an inversion to retrieve the coupling at depth. We use an Okada dislocation in a linear inversion. We impose the sleep direction for each patches, and we did the initial assumption that the model is coupled between 0 and 20 kilometers of depth. So then we obtain a map of sleep deficits that we need to divide by the velocity of plate for each patch to retrieve the coupling. So here is the result of the coupling by using only GNSS data. We observe a coupled region in the deep part of the subduction zone, the part of deep slow sleep event. And in the shallow slow sleep event area, we observe 2 patches of a null coupling or negative coupling here, which is expected because here we didn't take account of the slow sleep event during this observational period. So now if we had INSAR in our inversion, we observe that the coupled deep patch here is more correlated to the slow sleep events than using only GNSS data. Our inversion doesn't change a lot of things in the shallow part of the subduction because the INSAR data doesn't cover very well this region. Now if we compare a model using only INSAR and a model using only GNSS, we observe that in the Manawatu region, we would not be able to retrieve coupling using only GNSS data but we are able to retrieve all the coupling of these patches using INSAR data. So using INSAR allows us to obtain more detailed coupling map. So we did the same inversion for the 2 years observational period. We still observe a coupled region in the deep slow slip event area. So here we have a smoothing which is more important because we have more dispersion in INSAR data, and so we have bigger errors. We still observe some uncoupled patch here because there is still slow slip event we didn't take account. But we now observe a coupled area here because we took account of these slow slip events. So finally, we can wondering how representative are this coupling map of a long-term coupling. So we compare our results to a coupling map over 10 years using only GNSS data this time. And what we observe is we have a non-coupled patch in the deep slow slip event area. In the shallow slow slip area, we have also uncoupled patch, which is expected because we observed a lot of slow slip event during this time period. So finally, if we compare the sleep deficit over 10 years and the sleep deficit over 4 years, we are able to retrieve slow sleep events in the deep part of the subduction. If now we look at the amplitude associated with these patches, we retrieve an event with 18 centimeters of sleep, which is exactly what has been observed before. So finally, to conclude, we can go back to the beginning. So if deformation evolves through time, which observational period should we choose to recover plate coupling? There is probably no good answer because the interseismic period is not stationary in time and space, and we should probably be careful when we compute plate coupling over faults. Secondly, by looking at different time periods, can we determine a kinematic coupling? So comparing different time periods help us to observe which region can seismically slip and which other region doesn't slip seismically over a different time period. And finally, the spatial extent of coupling is directly linked to future seismic hazard, and thus GNSS provides sufficient resolution to accurately recover coupling. It's probably not the case even in regions like New Zealand where the network is very good. And we know that INSAR will probably not replace GNSS network, but it can provide a very essential information in our coupling estimation. And finally, if we are not able to retrieve slow slip events with INSAR data, like here, because we're missing the beginning of the event, we are still able to recover the events by comparing different coupling observational period. Thank you.
Okay, thank you very much. We've got time for some questions. There's a question over there.
Hello, thank you for the talk. So I had a question on the period between the major slow slip events. Did you select the images beforehand that you wanted to use and constrain the time period that way? Or were you able to detect such an event in the time series and then throw away the data that is not contained in the period of interest?
So here we are able to retrieve this event with our INSAR time series. So what I don't show, it's not this track, it's his track, but we were not able to use the velocity map because it was too noisy and we had too many unwrapping errors. So on the track I used to do the inversion, I do not observe the slow slip event signal. So I didn't trunk my INSAR time series. I just choose the period between 2019 and 2021 to do the trajectory model.
Right, so in a sense beforehand you select the periods that you're interested in for the whole
Okay, any more questions? I've got a question, if there's none in the audience. So, have you considered whether, do you think the data has enough power that you could resolve for the slip history on the fault? So instead of doing these fixed periods, just actually get a movie of which bits are slipping at different times?
Yeah, I think adding INSAR is very helpful for the depth part of the subduction, because finally the GNSS network doesn't go so far here. And with INSAR, we help the inversion to retrieve slip at depth.
And do you think you could resolve, if you took the fault patch,
Yeah.
And you took an individual patch, do you think you could resolve how much that fault patch slipped through time as a full time series?
I would like to do it, but there is still some seasonal signal in my INSAR data. But it's something we think about.
Okay, great. Any other questions? If not, let's thank Louise again. So the next presentation is a talk. Is going to be given by Raphael Grandin. This presentation prepared by Margaret Matte.
Exactly.
Okay, très bien. Nod on 15 minutes.
Okay, thank you.
Speak nicely and loud.
Okay. So hello everyone. So I'm gonna talk today about the deformation in northwestern Tibet, and use a Sentinel-1 time series to constrain slip partitioning, deformation, slip rates, arcing depths of faults in this area of that you see on the map. So it's between the Tibetan Plateau and the Tarim Basin. So before I start, I would like to acknowledge my co-authors, and especially Margot Matte, who could not be here, and that's why I had to step in. So first, the area of interest. So as I said, it's northwest Tibet, where there is a very well-known fault, the Altintag fault, that you can see here, and that delineates the border between the Tibetan Plateau and the Tarim Basin, which is much lower altitude. It's a desert with sand dunes. And we are interested in trying to constrain the deformation to the west of the Altintag, in this area here, where things are much more complex. There is not a single fault. You have several segments that split, especially the Karakash fault here, and the Longmu-Gozako fault. That's the main interest of our study here. There are also tiny volcanoes around here. And so it's an interesting region, because there is a considerable uncertainty about on the slip rates in this on some of these faults, and disagreement between studies that look at deformation over the Quaternary and more recent geodetically based studies. And in particular, this area here is very poorly known because it's very remote and because of high elevations. So we are interested to see how INSAR can be used to constrain the slip rates and seismic hazards of this area. And beyond the specific regional case here, we would like to design a method to be able to separate tectonic processes from other processes that we see in our images, as I will discuss in detail in the rest of the presentation. So we will use Sentinel-1 because it's a very powerful system to constrain deformation at these broad scales. It's still a challenge because we need to deal with a very large area. It's 1,000 kilometers wide. So we have to combine data from 10 different tracks, which is a challenge. There are large topographic gradients. Even if Tibet is a good area for INSAR, there are problems. There is snow, there are glaciers, there is some vegetation in the lower parts in the Tarim Basin, for instance. There are sand dunes. So all of this conspires to having many problems combined in our images. So to process all these data, we rely on a service that has been launched in 2020 that provides automatic processing of very large areas based on a selection of projects. So we had 8 projects. These are the red areas here in 2020, and then there are 9 projects that are currently being processed across the world. And so our primary target today is this one. So there is so the automatic processing is performed on the high performance computing facilities of CNES, the French Space Agency. We use NSBAS with tropospheric corrections to remove topographically correlated signals. And the result is a time series in the line of sight for each track in the area. So as I said, here we have 10 different tracks. So what we will do is that we will start from the time series for each pixel and try to go up to measuring strain rates or slip rates. So this will be basically the roadmap of the presentation, starting from now. So our first step is to mask the bad pixels, and for this we rely on the auxiliary information that is provided by the FlatSim service. So basically there is the number of interferograms, the time series inversion RMS, and the temporal coherence. So combining this information, we remove many pixels, especially in the Tarim basin. You will see that this is an area that we cannot really constrain. And then we reference all the tracks together, separate the signals between linear and seasonal components, then make an east-west, up-down decomposition, and then get to the tectonic interpretation. So first, the referencing. So we use GPS velocities that we project into the line of sight. So these are the colored dots that you see in these 2 images. So on the left-hand side, you have the ascending mosaic. That's the result of the mosaicing. And on the right-hand side, the descending. So you see that there are quite, well, the coverage by the GPS dataset is quite complete, but it's still relatively coarse. So that's showing the interest of having INSAR. So to perform the referencing, we just remove bilinear ramps in azimuth and range. And just by looking at these 2 images, we see very clearly that there is a contrast, in color contrast, about 5 millimeters per year in the line of sight. It depends, ascending, descending, across the Altin tag. And it goes to the west up to this area here that we will focus on. So this is a zoom on the left, on the western termination of this contrast that we see at broad scale. And so if we make a cross section across the fault here, this is what we have in ascending and descending. So here you have the ascending. Descending is on the previous slide, just for you to see. It's here. So what we see very clearly on the ascending is that there is a very sharp contrast. You can see here a step. Whereas on the descending, it's not so clear. So this looks not so consistent at first sight. So we will focus on this area, try to understand exactly if there are other processes in addition to the tectonic processes in this region. So I will focus on this diamond-shaped area here. And why is that? It's because it's a place where we have 4 different tracks that cover the same area, 2 ascending, 2 descending, so they all overlap. And so we have a very redundant information. And we try to understand what's going on. And to analyze the data in this diamond-shaped area here, we first remove a step that we believe is the block motion across the fault, about 5 millimeters per year, to be able to highlight the more high-frequency information and remove the broad-scale tectonic deformation. And so this is what we get if we remove the step. So to the left, on the left, you have the 2 ascending tracks, and on the right, the 2 descending tracks. And so what we see is that, so the block motion is removed, you don't see it anymore. It's supposed to be here. But in detail, you see very consistent patterns across the 4 geometries, and especially in this rectangular area here, you see that there are blobs that are not tectonically related. And this is showing this is the line of sight velocity, by the way, I didn't say it. And so what we try to do is to interpret in detail what's happening in this area and use it to maybe correct the interferograms and extract only the tectonically meaningful information. So what we do is that we extract the linear component of deformation plus the seasonal component of deformation for these 4 different tracks, and then we combine them together to have the linear component for the vertical, linear component for the east-west, and then seasonal terms. So that's what you see here. So to the left, you have the linear, so the velocity, mean velocity in vertical. Here you have the velocity on the east-west component. And then here you have the seasonal terms, but I show here only the vertical one because the east-west seasonal doesn't show any significant, meaningful information. So let's try to interpret the 2 maps on the left, the linear terms, vertical and east-west. So if you look in detail in this rectangular area here, on the left-hand side, you have the same information, but overlaid on topographic gradients, just to see what the topography looked like there. And what you see is that the blue areas, they are going down, and they correspond to topographic heights, so mountains. And if you look at the horizontal component here, you see it's red to the west of the mountains, and it's blue it's red to the east and blue to the west. And so the interpretation is that we have something that is moving downslope, but we see it only for mountains that are aligned north-south on the track, because we don't have any sensitivity to north-south motion. So our interpretation is that this is due to gravitational motion. And now if you look at the 2 other images here that show the seasonal term for the vertical, what we see in certain areas, especially in this area here, is that we have something that is going up and down in a flat area, and that corresponds to a basin, or at least some area that is between 2 mountains. So we interpret this as hydrological motion. And so we use this rationale to correct to say these are the non-tectonic processes that we want to get rid of. And so we use this specific example to apply a filter on the whole track. And so this is the result of the filtering. So to the left, you have the linear east-west velocity without any filtering. Then here you have the components that we believe in this map that are related to non-tectonic processes, and we decide where they are on the basis of the analysis of the topographic slope. So when the topographic slope is steeper than 30 degrees and the slope azimuth is aligned plus minus 30 degrees with respect to north, then we say that this is an area that we cannot really trust. It's probably corrupted by topographic gravitational motion. So we just remove it. And so this is what we get after adding back the step that represents the block motion across the fault. And this is the same map after removing non-tectonic processes. And we see that this map is much clearer and represents, we believe, with more fidelity, the tectonic component in our velocity maps. And so we expand this methodology to the whole track and apply it to the whole mosaic. So this is our final result. So this is an east-west velocity map for the 10 tracks merged together after removing these areas where we think that there is something that is non-tectonic that is happening. And then finally, we can make these cross sections across the fault at 3 different places. So across the Alpine tag here at the bottom. So here you have Tibet to the west, to the left, the south here, north here. And so we see a very clear, well-known arctangent pattern that we interpret as a slip at a rate of about 6 millimeters, 7 meters per year. I don't remember exactly the number from the top of my head. And a locking depth that is deeper than 10 kilometers. And then when we move to the west, profiles 2 and 3, through 2 and 1, you see very clearly that the gradient is much sharper, and then we end up having a creep across this Gozako fault here at a rate of 5 millimeters per year. So the conclusion is the transition from, there is a transition from localized deformation near this area, and then it moves into something that is more diffuse further to the west, and we lose the deformation around this 81 degrees longitude. And our secondary conclusion is that maybe the Caracas fault here is maybe less active than the LGC fault here, at least today, based on geodetic information. So these will be the conclusions of the study. So we were able to separate tectonic from non-tectonic signals by analyzing the patterns of deformation in topography and get to measure deformation, well, velocities at an accuracy of a few millimeters per year using this automated processing service. But this involves quite a lot of, still a lot of post-processing. So that's all for me. Thank you for your attention.
Thank you, Raphael. We have some time for some questions again. There we go.
Nice talk. How do you explain that you go from almost like 0 millimeter per year deformation to 5 millimeter per year, like in the diamond area, like very sharp, like no, you can go back to the last slide.
Last slide? This one?
Yeah, you have on the Longbow Cove fault, you have almost no deformation, and very quickly you go to like 5 millimeters at least. How do you explain that, like geophysically, like where does it go after the deformation, like before, on the western part?
The question is, how do we go from a very sharp gradient?
Yeah, I mean, I don't really understand like how, what kind of like process can explain like that very quickly the deformation dies when we go westward.
Change in speed. Well,
I have no simple conclusion. I mean, one possibility is that the locking depth goes deep quickly, but then if it goes too deep, then it's as if there is no fault anymore. So, well, there is no, I don't have any clear explanation for this. It's an observation at this point.
there was an earthquake roughly there, wasn't there? When was, I forget which earthquake and what year, but am I misremembering? I'll have to look it up. But I think there might be a bit of post-seismic that's still in the Sentinel data. And that would explain a little bit of it being faster.
Perhaps, yes.
Yeah, but I'd have to.
There is a slide where you have recent earthquakes shown.
There's another question there.
This one.
And then Eric afterwards.
Hi. So correct me if I'm wrong. So you're using a block model to calculate what the slip rate should be, removing that from the INSAR, and removing everything for it, and then adding the block model back in.
Yes.
And your final answer is the same as the block model. Is that?
No. Sorry, maybe I wasn't clear. The removal of a step function or a block model, in my view, is just for communication purpose. It's just to show you that if you keep the block motion in the images, you will not be able to see what I'm trying to explain. So we just remove it and analyze the residual and see that there is a systematic pattern that is related to topography. And so once we have understood this, then we go back to the original data without removing the block model and do the corrections. So no.
Could another approach be just to do a bandpass filter either side of the fault of all the data of anything smaller than a certain wavelength?
Well, if you do that, maybe you would just destroy a little bit of the signal, especially if it's really at short wavelength, like creep. So I would not advise to do that. Maybe by playing with the direction of, well, maybe we could try this.
Okay, I think Eric has a question, but you can see the earthquakes on the map, look.
Yes.
There we are, so there were some.
But they are not in
They're maybe not in the right place.
No. So these are mainly, by the way, it's interesting, normal fault earthquakes on the Ashikole segment. These are really big earthquakes, but they are not strike slip.
Did you look at the phase closure bias on these data?
It's one of the byproducts of the processing, but we didn't really look into it in detail. It seemed, well, still, I mean, geographically, at least, I can say that it was relatively negligible on the Tibetan plateau part of the area. But in the Tarim Basin, we had large biases. But in the end, we removed this area because the overall coherence is low. But we didn't really look into this in detail.
We saw the strong correlation with the phase closure bias of being different on the east and west sides of the ridges.
So what you imply is that maybe this signal that we attribute to gravitationary motion may be due to some bias. Okay, that's interesting. We could discuss this.
Okay, any final questions? Time for one more very quick question. If not, I shall pass over to you got one, sorry.
If no one else has one, I have one. I'm sorry if I missed this, but did your processing apply any kind of tropospheric correction, particularly to deal with topography correlated atmosphere signal?
Yes, it's part of the processing by FlatSim. We use the ERA 5
Okay.
ECMWF corrections.
Got it. Thank you.
Okay, I'm going to hand over to my co-chair to introduce the next speaker.
That would be me. So our next speaker is Natalie Forrest from the University of Leeds, who's going to talk to us about post-seismic deformation on normal faults.
Okay. Okay, hi everyone, and welcome to my. Is that okay? Welcome to my talk. My name's Natalie, and I'm a second-year PhD student here at the University of Leeds. So today I'm going to be talking about 30 years of post-seismic deformation of a continental normal fault as measured by multi-satellite INSAR time series. So I've been using 3 different generations of SAR satellites, so ERS, Envisat, and Sentinel-1, and I've been using the resulting INSAR time series to be looking at the dynamics of historically understudied dip-slip faults. So the last talk was quite a good example of how historically we tend to look at strike-slip faults and tend to overlook dip-slip faults a bit more. So by creating a 30-year time series, I hope that we can look at like the later stages of the post-seismic deformation. And again, a lot previous studies tend to look at the first few years of post-seismic. And unfortunately, I have to mention the magnitude 6.8 earthquake in Morocco on Friday. It just demonstrates how dip-slip faults are capable of producing a large amount of devastation. And this is particularly true in an area such as in Morocco, where you don't tend to get such large earthquakes as often, and so the population is generally underprepared. So hopefully by doing further study into dip-slip faults, we can better understand the dynamics and then communicate the hazard in future. Okay, so to start off with, I thought we'd look at some normal faults in the field so we can get an idea of the scale of the deformation that we're looking at. So here's a normal fault from the Gulf of Corinth in Greece that I took on a field trip. And here you can see the normal fault trace along the base of this hill. And over multiple earthquake cycles, the footwall has uplifted several hundred meters and the hanging wall has subsided down into the valley. This is similar to the fault that I've been looking at in Greece, so it's a similar geological and tectonic setting. However, this is not the fault I've been looking at. And then we also have this picture from Italy, from Laura Gregory. And so this is from the 2016 Central Apennines Italy earthquake sequence. And this picture was actually taken 2 days after the 30th of October earthquake. So this is like very fresh slip on the fault. And you can see the person in the background is like 1 to 2 meters of slip. Okay, so just to go through a simplified earthquake cycle model. So this is looking at like a one-dimensional how stress accumulates on a fault over time. So firstly, the fault will break in an earthquake when the maximum strength is reached. And then there'll be this very quick drop during the co-seismic deformation period, so the earthquake. And then the section of the earthquake cycle I'm interested in is this faster post-seismic recovery time. And here the stress will recover slightly faster, but then over time, this will decay to a slower interseismic deformation rate. And then this cycle will repeat over multiple earthquake cycles, and you'll get variable earthquake size and also repeat times between them. However, this is based generally on strike-slip faults, and the strength of the fault might vary through time, and also the geometry might be a bit different when you incorporate dip-slip faults. So yeah, earthquake cycle models tend to be based on strike-slip faults. So you have this very simple idea where you have this constant simple geometry which will go for thousands of kilometers. And these faults also tend to host quite large earthquakes. As we saw with the Turkey earthquakes in February, these were up to magnitude 8 almost. Additionally, we tend to have quite fast slip rates on strike-slip faults. So there'll be up to tens of millimeters per year of deformation. So the real question here is, do earthquake cycle models, can they also be applied to dip-slip faults? So the general aim of my project is to study normal fault dynamics, so take concepts about the earthquake cycle from strike-slip faults, combine this with 30 years of geodetic observation, so primarily INSAR, and then see if we can better understand normal fault dynamics through time. So there are two primary post-seismic mechanisms on dip-slip faults. So firstly, you have afterslip, which occurs on the fault interface around the co-seismic slip patch. So this can either be seismic slip in aftershocks, or it could be aseismic slip, which won't produce aftershocks, but you'll still get slip on the fault. Additionally, you can have viscoelastic relaxation. So there, as you go below the fault zone, the rocks are actually hot enough to flow on longer timescales. And this viscous flow occurs over several years, depending on what the viscosity of the material is. So during the earthquake, there is a stress gradient imposed elastically on this area, and then these stresses are relaxed as the rocks flow over time. And talking a bit more about viscoelastic relaxation, there's two end-member models of this. So you can either have broad deformation, so this is a distributed longer wavelength flow throughout the high viscosity ductile substrate beneath the fault. And with this, if we link it back to INSAR, the expected surface deformation is that you get a broad zone of post-seismic uplift around the fault. Alternatively, there could be a narrow zone of viscoelastic relaxation. So this could be focus flow directly below the faults, where you have a slightly lower viscosity, and it could be like a down dip shear zone. With this, we expect a much narrower zone of post-seismic uplift around the fault. So how did I pick which normal fault I wanted to look at in more detail? Firstly, INSAR doesn't really work so well over water, so I wanted to pick an earthquake on the continents. I wanted also to be able to measure a significant amount of post-seismic deformation, and you tend to get this with larger earthquakes, so I've filtered for ones that are bigger than magnitude 6. And looking at the INSAR that's now available, I wanted an earthquake that happened about 30 years ago so that you can look at both the very early post-seismic and also the later post-seismic, so looking 30 years around now as measured with Sentinel-1, see if we can link those observations together. And additionally, we wanted an area where there's good INSAR coverage, so with the C-band, you're not necessarily going to get good coherence on the scale that I'm looking at, where there's glaciers and vegetation. And it'd be good if there's some GPS around to help ground truth our measurements. So I've settled on choosing the Grevena earthquake, which was a magnitude 6.5 in May 1995. So this is an ERS interferogram created by Tim. And so yeah, there's quite a few co-seismic studies on this earthquake. The main fault strikes west-southwest, dipping to the north, with basically purely normal fault motion. And there was a couple of meters of slip at 6 to 15 kilometers along the fault, and there was this shallow slip deficit. Additionally, there was this GPS campaign, which is really interesting. So you can see in the first 4 months of post-seismic, there was roughly 8 centimeters of displacement measured on the fault, and this was primarily after slip, we think. And then throughout the rest of the year, there were still centimeters of deformation displacement happening. So yeah, as I mentioned before, the previous studies on dip-slip faults tend to focus on the very early post-seismic. However, now the INSAR data is available for nearly 30 years. So this is a conceptual timeline of how the Grevena post-seismic deformation may have evolved through time. And the geodetic techniques I'm going to use are the GPS campaign, ERS 1 and 2, ENVISAT, and then Sentinel-1 and Sentinel-B. 1A, 1B. Okay, so the GPS campaign and ERS should look at this early after-slip periods. ENVISAT might be able to show us some later viscoelastic deformation through time. And then as we're getting into Sentinel-1 and close to the present, the real question is, has the deformation finished, and would we be able to see if it has? So yeah, my aim is to build this really long-term post-seismic time series. So this is a co-seismic interferogram that I've created using gamma. So this shows the co-seismic deformation and also the first 3.5 months of post-seismic. It's a north-dipping normal fault, so you can see there's a lot more deformation to the north of where I've marked the fault. There's roughly 12 fringes, so this represents 35 centimeters of displacement in the line of sight. Sorry. And there's also ERS interferograms which show very early post-seismic displacement. So this interferogram spans 6 months to nearly 2 years after the earthquake. And there's 1.5 fringes here, which you can see it go from purple on the fault, going back out to purple again, which represents about 4 centimeters of displacement in the line of sight of the satellite. Here there's a very sharp interface, and the length scale of the deformation is about 10 kilometers. So this represents early afterslip. Okay, so here's a network that I've been building in order to create an ERS post-seismic time series. So here's all of the SAR acquisitions for the descending frame over Grebner. And after 2000, we had the gyroscope failure, so I haven't been including that in my time series for now. And yeah, so there's a lot more spread with the perpendicular baseline and the temporal baseline compared to Sentinel-1, which tends to be 6 to 12 days, repeat time, and a couple 100 meters probably at most for the spatial baseline. So I filtered for interferograms which have a temporal baseline of less than 3 years and a spatial baseline of less than 300 meters. After running all of the interferograms which fit those criteria, which are highlighted in gray, I've got 6 interferograms which show good coherence, and I've put these into a small baseline inversion in stamps, which just has the effect of reducing the noise and increasing the coherence. And here's the resulting time series, which shows quite a strong signal of post-seismic deformation. There's roughly 10 millimeters per year on average of line of sight displacement in the hanging wall subsiding, and also slightly less than that in the footwall uplifting. So this spans from 4 months after the earthquake to 4.5 years after the earthquake, so roughly 4-year time series. And there's, again, a very sharp interface around the fault, and the deformation extends 15 to 20 kilometers north of the fault. So this is probably predominantly after slip, but there could also be some very early viscoelastic relaxation happening there too. Okay, so that was ERS, and now I'm moving on to ENVISAT and processing the post-seismic time series for that. So this is a single interferogram, which is from 11.5 years to 12 years after the earthquake. And you can see the fault is roughly located where the arrows are. You could maybe convince yourself there's a bit of a discontinuity happening there. You can't really make any strong conclusions because there's quite a lot of noise. So I'm now constructing the time series for the ENVISAT interferograms using the same criteria for spatial and temporal baseline as ERS. And these are all of the interferograms which fit that, and the green ones are the ones which have good coherence. So it's not quite as good as ERS, but I'm going to process those in the future and create an ENVISAT stamps time series. Moving on to Sentinel-1, I've created a time series using the LixBus software, and it doesn't seem to show any displacement at the moment. So this is 19.5 to 26.5 years after the earthquake, and there's no measurable post-seismic deformation around Grebner. So does this mean that the post-seismic deformation has now finished? Or is it just that post-seismic isn't necessarily observable 20 years later within the uncertainties of INSAR? We've also had quite a few talks about the European Ground Motion Service, so I've had a look at this. And again, it really doesn't look like there's any measurable deformation using Sentinel-1 in this area. Okay, so bringing all my observations together, the question is, does the decay of post-seismic deformation, is it more exponential or does it fit a logarithmic trend? So we have roughly 10 centimeters a year measured in the first year of the GPS campaign, which plots around there, and also 10 millimeters a year of displacement measured by ERS, which fits roughly around there. Oh, sorry. So at the moment, it looks like it's more of an exponential decay rather than a logarithmic decay, but we'll take the ENVISAT data and see if that can help us better understand the long-term time series. Okay, so to summarize, I've been creating this 30-year time series of post-seismic deformation on a dip-slip fault. I've been using 3 generations of STAR satellites to measure the post-seismic deformation following the magnitude 6 Grevena earthquake in 1995. By generating a 30-year time series, hopefully we can better interpret the relatively understudied dip-slip fault dynamics. And next, I'll run some forward models to see if you can distinguish between whether there's narrow or broad viscoelastic relaxation, and then further compare this with strike-slip faults. Okay, thank you for listening.
Thank you so much. We have time for questions. Yes.
Hi, thank you very much. That was truly interesting. So I have 2 questions, if that's all right, both related to how the displacement at the surface relates to the strain at the fault, at the contact. So I can imagine if you have movement across the fault, or you have slip, that relieves strain, at least that I would imagine so. So if you have, for example, slip right after the earthquake, after slip, I believe you called it, does that relieve strain over you had this conceptual curve where you had a sharp drop in strain during an event, and then you had a gradual buildup of the strain before the next big event, right? So if you have after slip, how does that relate to this buildup of the strain?
So it depends on the actual geometry of where the slip is. If it's around like a locked area, then it could potentially reload that section of the fault. But if it's on the actual co-seismic slip patch, then maybe it could build up. It depends if it's, yeah. If you're looking at 1 dimensions or 2 dimensions, it gets slightly more complicated. But yeah. Did you have a second question?
Okay, yeah, no, that's all right. But I have a follow-up that's related. So if you have a look at the Sentinel data, let's say, and you say there's not a lot of movement anymore, does that also necessarily mean that there's not much strain buildup anymore? Because I can imagine that there is still strain buildup, it's just waiting for the next big event, let's say, right? But how do you tell how far you are to the next big event if you are looking at displacement, and it's a proxy for strain in a sense, right? Do you get my question?
Oh yeah, I see what you're saying. Yeah, I mean, I could probably try and calculate what the strain across the region is as well. But at the moment, just saying it's 0 velocity.
Sorry, actually, I said strain. I meant stress. Sorry about that. It's, so if there's stress buildup in the fault, then you don't see it in the displacement, right? But the more stress there is on the plane, the bigger the next earthquake might be, or the more likely, I guess. So, yeah, I guess the question is, how do you relate the displacement to the strain on the fault?
Yeah, so one way we could do that is by running some forward models and then seeing what the stress could be at depth and then what the resulting expected surface deformation is. Or yeah, you could look at the strain potentially. But some of these displacements are quite small, so I don't know if you'd be able to like have a very good idea of how big the stress changes are and like whether it changes over time. But yeah, it'd be quite hard to, because you don't necessarily know when a fault has finished building up stress until the earthquake happens. So I don't know if the rate of stress accumulation would necessarily affect how big or how quickly the next earthquake is.
In a sense, that's like the million.
Yeah, yeah, exactly.
Okay, thank you very much.
Thank you. Anyone else? Yes.
Hi. For the ERS process, you only showed like a mean velocity map. Did you look at the time series? And in your time series, can you see the decay of the displacement? Do you have enough like observation to already see a slowdown of the velocity?
Sorry, what was that? The coherence?
No, like you only.
Oh, I see.
Can you already constrain the shape of your deformation with time, with the time series? Because you can't do it with only the mean velocity map.
Yeah, so at the moment the map just shows the average displacement, so it's basically interpolating a straight line. But yeah, the individual time series, I'm working on averaging them because there's a reasonable amount of noise, but we know that there's a good signal. So yeah, hopefully by, as you say, looking at the time series in a bit more detail, we'll be able to actually constrain the shape of the decay.
Great. Any more questions? We have time for about, yeah, go ahead.
Some of these normal faults are routed into a décollement, and so there is a change in the dip angle when you get under the seismogenic depth, let's say. So to what extent would you be able to capture a tiny slip occurring in this décollement, on this décollement, at the same time as you have after slip at shallow depths? To what extent does the slip at shallow depth may hide some signal routed deeper into the fault?
Yeah, so it's quite difficult to tell the difference between like deep after slip or slip on in a shear zone at depth. So yeah, at the moment probably a lot of the ERS signal is overprinted by shallow after slip, but if we're able to run some models, we could maybe do like a sensitivity test to see if you can actually tell the difference. You might not be able to, but we could see. But yeah, good point.
One more question.
Yeah, thanks for an interesting study. No, I wouldn't disregard all the post-2000 ERS data, because you can pick seams or pairs with similar kind of double shift, and then you could have a disconnected network. So it's something you could try. But the question is, I mean, how long is your PhD? Can you put up a continuous GPS right in the middle of the subsurface pole?
It was suggested. But yeah, it's quite expensive to go out there and put a GPS station. But yeah, we'll see. There might not necessarily be enough slip over 4 years. So yeah, I have another 2 years of funding. But yeah, we'll see.
Oh, yeah. Should we? All right, one more. Last one.
Last one?
Yes.
Well, it's a good occasion. Yeah, very nice talk. And, but you began by mentioning the Moroccan earthquake, which is a thrust fault.
Yep.
And it's a thrust mechanism. Do you think that you would do the same job for the thrust faults in general?
Well, thrust faults, it was kind of 50-50 whether I chose to look at thrust faults or normal faults.
50-50.
Because they're both dips of
50-50.
faults. But yeah, thrust faults tend to be a bit larger than normal faults. But other than that, we have the data available for the 30 years, so we should be able to come up with some similar ideas.
Yes, well, there are many thrust faults around the world. And one thing to go to along with the question on the strain and stress, of course, the mechanical behavior between the thrust faults and normal faults are totally different, right?
Yeah, they probably behave quite differently, but I have focused mainly on normal faults.
How much time you have left for your PhD?
Look at every thrust and normal fault.
Thank you, everyone, for the great discussion. Thank you for the good talk. Our next speaker is Leo Marconato from University of Grenoble, and he's going to talk to us about Sentinel-1 time series on the North Andean Slur.
Thank you. Good afternoon, everyone. So I'm Leo Marconato, PhD student at ISTER, Université Grenoble-Alpes, and I will talk to you about part of my PhD project on the observation of North Andean sliver motion using INSAR time series analysis. So to locate a little bit the study, we are looking at the western coast of South America in Ecuador and Colombia, where the Nazca plate is subducting below the South American plate at about 5 centimeters. It's not close enough. At about 5 centimeters per year. And this subduction motion is actually oblique, as you can see on this map. And this obliquity causes through partitioning of deformation, causes the individualized motion of a block, continental block that we called the North Andean sliver, that is in red on this map. This block is moving at about 1 centimeter per year towards northeast with respect to stable South America. So more precisely, we are here looking at the western part, the western boundary of this block that was shown to be the deformation of the block, of the western part of the block is mostly localized on the fault system called the CCPP fault system, standing for Kosanga Chingwal Payatonga Puna fault system. And that's where we are focusing in this study. Very recently, first attempt of block modeling at the scale of Northern Andes was published by Harin et al. And is proposing a geometries for several blocks within the North Andean sliver, especially, for example, this Quito Latacunga microblock that is individualized within this western boundary. So this was constrained using only GNSS data, but we thought that adding INSAR with higher spatial resolution in such an initiative could be very interesting. So that's what we tried to do. So, however, INSAR is a rather challenging technique to process in this area for several reasons. We are in a very mountainous area with strong topography and strong elevation gradients that can make the processing complex. Also, we have dense vegetation, especially in the lowlands, where it's mostly equatorial forest because it's very wet, and this vegetation can totally make impossible the processing of INSAR. Moreover, even at high altitudes, we have often cultivated lands because there is no snow even at 4,000 meters in Ecuador. Also, we are not so far from the subduction that causes tectonic events. I will talk a little bit more about this later. And with all these issues, we are also looking at not so huge deformation rates. We expect a few millimeters per year in the line of sight of the satellite. So it's on the edge of the detection threshold of INSAR. However, using Sentinel-1 and the large archive that is available now, we could process some results. So this is the data I processed. So I used 3 tracks in this area, 2 ascending tracks and 1 descending track. And we used the full archive of Sentinel-1 since 2014, so it's about 8 years of data that represents 200 to 300 acquisitions for each track. However, we were not able to process velocity map on all this image coverage because of problems of coherence due to vegetation. You can see that on this interferometric coherence map, there is a bimodal distribution on the lowlands. The coherence is very bad due to dense vegetation, while on the Cordilleras and the high elevations, the coherence becomes medium to sometimes very good, and then we are able to process. So the area we could really image is the intersection of this good coherence area on which we could unwrap up to 1 year interferograms. So it's about 2,000 elevation, 2,000 meters of elevation, and also the area where we could have two viewing geometry. So it's an area of about 100 by 400 kilometers. Regarding the processing strategy we use, so we use the NSBAS processing chain developed in Grenoble, which is an NSBAS strategy. And we took care of the proportion of long baseline interferograms that we included in our interferogram networks in order to mitigate as much as possible fading signals. Another issue that we faced is that in 2016, so in the beginning of the period of acquisition of Sentinel-1, there was large megathrust earthquake on the coast of Ecuador, namely the Pedernales earthquake that was magnitude 7.8. And that produced, as you can see on this GNSS time series in Quito, a large seismic displacement, even very far from the coast. So in Quito, we have about 6 centimeters of displacement towards east, which is not negligible. And moreover, we have a non-negligible post-seismic deformation. So in the first, we divided this post-seismic period in two phases. So the purple one that is very non-linear, and the yellow one, the orange one, that is more or less linear at the scale of the 5 years on which we had Sentinel data. And you can see that even on this second post-seismic period, we have not, there is still a difference with the velocity before the earthquake. So we are still undergoing post-seismic deformation, even if it's roughly linear in time. So the strategy we adopted, as we have not enough Sentinel-1 acquisitions before the earthquake to derive a robust velocity, is to compute this velocity on the third period, on the yellow period, and then to correct using GNSS this velocity to retrieve the interseismic deformation. So our workflow basically was to compute interferograms using the NSBAS processing chain and ERA5 tropospheric corrections. We also optimized the weighting of pixels during multi-looking using temporal coherence to overweight the stable pixels, also to avoid to mix biased pixels due to phase closure into the multi-looking. From those interferograms, we computed the time series of deformation, of loss deformation. And for each pixel of this time series, we extracted a linear velocity in this orange period, so the period where the post-seismic effect of the Pedernales earthquake is mostly linear. So it's the period starting in mid-2017, so about 1 year after the earthquake. Then we referenced our velocity maps into a stable South America reference frame. To do so, we used GNSS time series extracted on the same period as the INSAR velocity map. And then we decomposed the ascending and descending geometries into east plus vertical components after removal of interpolated north component of GNSS reflected in loss to a straightforward decomposition. And finally, the last step is to correct the velocity map from this post-seismic effect. So we know, as we have GNSS velocity before the earthquake and after, we can make the difference and interpolate it and remove it from the INSAR velocity map to have an equivalent interseismic deformation map. So here are our results. We compare them to the prediction of the block model published by Harin et al. This year. So here it's only for the east velocity, as it shows most of the tectonic deformation, and as the vertical is much more noisy. So we'll focus on the east velocity. On the left, it's the prediction of the block model, together with the GNSS velocity field that was used to build this model and the fault geometries that were used. And on the right, it's our results, so the velocity map for the east component with the same color scale. It's at first order, you can feel that it's about a good agreement, but to look into more details, I made a series of profiles that are perpendicular to the main faults of the area, on which we will be able to see a little bit more precisely. And so here are the profiles. So the white envelope represents the velocity of the block model. The point cloud is the INSAR data, and the dots are the GNSS velocities, so before the Pedernales earthquake. So overall, we have a good agreement. The integrated gradient over the Cordillera is well constrained by INSAR, or at least it's in agreement with the GNSS and with the block model. And even in some profiles, such as the 6, 7, 8, this one and those two, we have some gradients on main faults that are constrained by GNSS, and so that are shown in the block model that are reproduced by the INSAR velocity maps. However, in some other profiles, such as this one and this one, the 3 and the 9, we have large discrepancies that we interpret as simplifications that were made in the geometries and coupling state of the faults during the block modeling, because it was also a block model made at the scale of whole northern Andes, and because GNSS spatial density was not able to resolve these parameters either. And so we think that now, on this kind of example, INSAR will enable better resolution to improve this block model, and it's something that we'll probably work after. So to conclude, we produced the first INSAR velocity map of the Ecuador-Colombia Cordilleras using Sentinel-1 data. We developed a strategy to correct the results from the post-seismic effect of the Pedernales earthquake using GNSS time series. And the results show good consistency with GNSS velocity and with the block model. However, this block model will probably be refined by the spatial resolution brought by our velocity map. Thank you.
Thank you. We have plenty of time for questions. Who's first?
I can start, I guess, if there's no other questions. So if you go back to your comparison of this figure. So I guess around profiles 8, 9, it looks like it's more red. It's further east.
Yep.
So have you got an idea of what geological structures might be responsible in that area?
So it's about the same area as the profile 8, 9. It's more clear on the profile 9 here, where we have a strong gradient that is further east of the main structure, that is the Payatanga fault that was seen as the main structure of the area. And actually, it's also a structure that is rather important in the morphology and in the geology of the area, that is called the Peltetec fault. But that was not extensively studied because the Payatanga fault produced to be a large earthquake in 1797, I think. And so it's the main structure from what was known from paleoseismology. But the other one could be a parallel strand or something like Ornithron fault that could be probably accumulating more deformation right now, at least.
Looks like there might be an inconsistency between the INSAR and the GNSS there as well.
Yeah, indeed. What we are trying to think is that we have another inconsistency on the Quito profile. So GNSS on the profile 5 on the left fault, you can see that GNSS and the block model were predicting creep on the Quito fault system that we are not resolving at all in our velocity maps. And we start to think that maybe the assumption we made that the interseismic long-term motion and the post-seismic effect are not totally independent, and that this post-seismic strain is probably modifying the behavior of faults. That's one of the hypotheses we can do now.
Great, thank you.
Thank you. Yes, I have a question up there.
Okay, thank you. As the area that you were processing was highly decorrelated, I was wondering how effective was the use of long-term interferograms in dealing with the fading signal. I mean, were they coherent enough to provide some information to mitigate this bias or not?
Yes, the answer is that on the area on which we process the map I show you here, the area that is shown is area where even the one-year interferograms were unwrapped without problems, without unwrapping errors. Like the coherence is sufficient to really have all the one-year interferograms totally unwrapped and robust. So we think that they are constraining enough the network to avoid phase bias.
So I have a related question, actually. So in these mountains, presumably you have snow. Did you look into the individual dates and interrograms to see if that's causing some of your errors?
I'm not sure I understood you.
You'd have snow on these mountains,
No,
so in some
I think
periods.
you misunderstood this. So I told you opposite. We have no snow at all, except really at the top of volcano. There is no snow below 6,000 meters or something like that. So snow is not a problem in Ecuador.
Great. Any other questions? Okay. Oh, Eric, go ahead.
Did you look at any L-band data?
Yes, I have a poster about that. I tried to process ALOS1 data before in Ecuador. And for that, we had to develop a ionospheric compensation procedure because the ionosphere was huge and very turbulent. However, given to the number of acquisitions in the ALOS archive, like about 20 acquisitions, it was not enough, even with the ionospheric correction, to derive velocity resolving 3 or 5 millimeters per year of deformation. We were able to monitor some volcanic inflation if it was several centimeters per year, but not millimetric precision.
Thank you. Any more? All right. If not, thank you very much.
Thank you.
We're going to move on to our next speaker, who is Dohua Wang from the University of Leeds. He's going to tell us about strain accumulation along the Altentag fault.
Okay. Hello everyone. My name is Dohua Wang, and I'm now a PhD student in University of Leeds. And today I'm very happy to share the information about the strain accumulation along the Central Eastern Altentag fault. Yeah, thanks to the second presenter, we know that what happened along the Central Western Altentag fault. Now let's talk about Central Eastern Altentag fault. So. So we know that there are some large-scale structural faults in the Earth's crust, and these faults are responsible for a significant portion of the world's earthquakes. And the well-known examples for such faults include the San Andreas in California, and also the North Anatolia fault in Turkey. But today, let's talk about the Altentag fault, which is also well-known structural fault working as a boundary between the Tarim Basin and the Tibetan Plateau. Previous INSA research have achieved some results based on the data from ERS, Envisite, and Sentinel-1. But most of these results are focused on relatively small areas. So leaving the question about how the strain accumulated along the fault unresolved. So we processed the data covering the whole Central Eastern Altentag fault. And we, besides revealing the strain accumulation along the fault, we also, we processed the data and we generated a 3D velocity map with high spatial resolution cover this area. And we will also use this velocity map velocity field to generate straight array maps. So besides revealing the string accumulation along this fault, our results also have other applications. For example, we can use this to localize the shell zone location, localize the shell zone, and we can use this to help us understand the deformation pattern around the active fault bands. And we can also use this to evaluate seismic risk and understand regional mountain building. So we know that to get a better velocity field, we must have better data. So we collected the GPS data from 1998 to 2021 from the CMONOC project, and we processed the data and we obtained the 78 3D GPS velocities. So these velocities are brand new and haven't been published. And compared to previous velocities, our velocities are 3D. It's unique. And also, compared to previous velocities, our velocity will have a lower uncertainty because we have a larger time span. And also, we include 17 published regional GPS velocities because we can't get this velocity. So we use this to let our velocity be better constrained. So we processed and acquired our data based on the Comet-Lix Sentinel-1 portal. So this is a frame-based automatic INSAR processing system, and all the interfragment in this portal is produced using the IXA processor, and all the products are multi-locate to a resolution about 100 meters. So and we use geckos to correct the atmospheric related noises, and also we use XBus to do time series analysis. And more details about this can be found in the website. So in this research, we include 7 ascending track and 6 descending track, and we totally processed 20 frames. And for each frame, we used nearly 180 epochs between October 2014 to July 2022. So we know that normally LIXA generate interferograms between epochs and 4 consecutive epochs, both forward and upward by default. But in this research, we choose to use a very densified network combining a normal LIXA network with 1 year to 7 year long temporal summer to summer baseline. So this will help us to reduce the potential phase biases related to relatively shorter temporal baseline. And we also want to use this to reduce the impact of the snow cover in winter because we want to know the signal on the mountain top. We need to understand the mountain growth. And finally, this kind of network is compatible with our aggressive notified strategy. So this table shows the statistics of all the ascending frames. So you can see that we use about 2,000 differograms in each frame. So it means that totally we processed about 35,000 diffograms in this project. So let's talk about unwrapping errors because this is very annoying. So normally in LIXBus, we use the loop closure phase of 3 images to identify the unwrapping error. So it means that if the loop closure phase is near 0, it means that there's no unwrapping error. But if it is integer multiples of 2 pi, it means that there are some unwrapping errors. So normally in XBus, we just abandon the whole interferogram based on the RMS of the loop phase images. But this will generate some problems. For example, we will abandon a lot of interferograms and generate some gaps in the network. And also, the abandoned interferogram will have some good data. And also, the kept interferogram is not perfect, still have some unwrapping errors. So we want to solve this time once for all. So we use another method. So we just abandon all the pixels in the interferograms that are related to unclosed loops. It means that we only keep the perfect interferogram in the time series for each pixel. So what is perfect interferogram? It means that all the loops related to this interferogram should have a loop closure phase of 0. So based on this method, we can see that before this method, we have a lot of unclosed loops in the frame. But after this, all these unclosed loops are bit zero. We don't have this problem. So we have escaped all the unwrapping errors. We keep more interferograms. We have better coverage. Also, we have a lower uncertainty in the final velocities. So this is our workflow. So we use Lixar generate interferograms, and then we use Lixbus combined with geckos and plane motion correction to generate line of sight velocities. But we know that these line of sight velocities are independently referenced. So we use VLMAP to do the velocity field inversion. And in this inversion, we try to remove the order reference frame adjustment ramp. And also we try to remove linear with height, atmosphere, noisy. So after this, we will go to reference line of sight velocities. And we know that if we want to do the decomposition, this equation is unsolvable because we have three unknowns. So we use the north to south velocity field model from VLMAP to constrain the north to south velocities and got our east velocity and the vertical velocity. So this is our 3D velocity models. And we compare this with GPS state, and it shows that the average of the difference is about 0, and the standard deviation of the difference is about 0.7. It's very low compared to the uncertainty of the GPS state itself. And this is our final ascending and descending date velocities, and this is our east velocity. So from this velocity, we can see this left lateral motion along the fold very well. And we can also see that how this left lateral motion diminishes at the east end of the fold. And this is our vertical velocities. So we can observe some short wavelength noise substance related to permafrost, but we can also see some long wavelength uplift related to tectonic motion. For example, the uplift in the Arton Sound range, and also the uplift inside the Chilean Langsang thrust belt. Yeah, when we zoom in this velocity field, if we use some profiles across the major restraining bands, we can see that all these bands are uplifting, except some short wavelength substance related to permafrost or landslide, suggesting that there is a very high compression and causing regional uplifting around this band. And also we can see that there's a higher uplift at the inside corner of the band. All this shows that there's a higher uplift inside the inside corner of the band. So this is consistent with previous research, which showed that the strongest shortening should happen within the inside corner of the band. So if we not believe that this is tectonic motion, we can also use some finite element modeling to show that. So if you build a finite element modeling, we will show that we can observe some uplift at the inside corner. So it means that this is due to tectonic motion. Let's talk about strain rate. So we calculate all strain rate maps using the gradient. And this is the maximum shell and dilatation. So from this maximum shell, we can observe the shell are just located on the Argentine fold. And we can see some relatively high shell rate around the restraining band, the biggest restraining band. And we can also see how this shell strain become absent at the east part of the fold. And also, we can look at the dilatation. We can see there is a very high compression inside the quadrant basin. We can also see some short wavelength compression inside the Chilean Langsang thrust belt. And this compression just located at the fold, some fold, so it reflects the shortening on the fold. So we can also look at the secondary variant. We can see that most of the high strain rate are just located at fold. So this we can use this to localize the shear zone. And we can also use this to estimate the dipping angle of the fold. And yeah, you can also, this is not very linear. So you can see some places near the fold also has a very high strain rate. It will reflect the width of the shear zone because of the branches that are parallel to the main fold. Some branches parallel to the main fold will cause the width of the fold is changing. Also, let's look at the beautiful map. If we zoom in this area, we will find a very beautiful strain partitioning at this area. So this has not been well revealed in previous research. But in this strain rate map, we can see that how the strain partitioned along other fold. We can see most of the strain rate accumulated along the Danghe Nanshan fault, and also accumulated along the Yama River Daxueshan fault, and a very little strain rate accumulated along the North Altai fault. So that's very important because in previous GPS research, we cannot identify that. For example, if we use there's a profile A across this area, which we think that have strong strain partitioning, then we have got a slip rate for this area. But the problem is that now the story is different. If we use GPS, we cannot identify that. So we are thinking that all the strain accumulated on the North Altai fault. So we calculate slip rate, and we will get a very high slip rate, about 3.8. Now, but also, even we know that there's another fault, the GPS can also do that because it cannot calculate the slip rate because they are too small. So with the INSAR, we have the chance to calculate slip rate on these two folds separately using some profiles across these two folds. And we can use some Bayesian inversion to calculate slip rate. So we can get that slip rate on the North Altai fault is about 0.9, and slip rate on the Yama River fault is about 2.4. So, and yeah, you can also look at the profiles. Yeah, this kind of destructive motion actually exists. So, is there any other research to prove our result? Yes, we have. So this is a result published in 2015. It shows that the slip rate on the Yama River Daxueshan fault is about 2.8 millimeter per year since the last Pleistocene. So this 2.8 millimeter per year, okay, is very consistent to our 2.4 millimeter per year. So it means that this strain partition is happening, and we have consistent result. So this we can do the Bayesian inversion for all of profiles along the fault, and we can show that the spatial variation of the slip rate, locking depth, location of shear zone, and also for specific polygon profiles, we can also estimate the creeping rate. Yeah. So there are some conclusions. So we think that a pixel-based aggressive notify method can use to remove the unwrapping error. And we have a 3D velocity map, and we can use this to reveal the spatial variation of strain accumulation and mountain growth. Yeah, we think that there are some important strain partition happening along the central eastern Altai fault and should be carefully considered. But that is not the whole story. Now, let's compare this with all other researches. And we see that the red diamond is our interpretation, and the other previous result, our result, and the pattern of our result will be shaded using some color. And we will see where the slip rate decreases, where have the slip partitioning, and where have some slip transfer. But yeah, we do have more details to show, and I'm welcome to have more discussion. Yeah, I think that's all.
We have time for some quick questions. Yes.
fascinating talk, and thank you for showing such incredible data sets. I'm wondering whether if there have been any historical earthquakes on this fault and your variation in the strain rates along it, if there's any special relationship between the two?
Shift to the what?
So historical earthquakes along the fault.
Old earthquakes, no. Since the last 100 years, there is only a very big earthquake happened. Yeah, we can show that in the first figure. Yeah.
Thank
you.
you.
Can see that there's only one strongest earthquake with a magnitude about 7.5 happened along the near the Yama fault, the Chama fault, sorry. And the other earthquakes are not too strong. And we can see more earthquake happen near the Australian band. And yeah, not very big earthquakes.
Thank you. We have time for one more. This is the last question. No pressure. Anyone? Okay. Here you go.
Curious, following some of the other talks earlier, they're also looking in similar areas and further along. Have you seen any of the east-west slope correlated signals in the horizontal on either side of the fault in your area?
You mean some east, west to east? I'm not follow that.
So have you seen any signals which are, say, I think eastward motion on the east side of slopes, westward motion on west-facing slopes, as we've seen in some of the other presentations today?
I haven't catch that signal in this research.
Thank you.
All right. Thank you very much, everyone. Thank you to all the speakers and all the discussion.
Thank you.
I just want to say that we're going to give this room up for a roundtable related to the displacement and deformation sessions, but our roundtable is going to be tomorrow after the other two tectonics and earthquake sessions, and we have plenty of discussion questions for you that we're curious to hear about, so please come.